3 on ordinary differential equations. So this particular examination was divided into two sections, section A and section B. In the section A, which contained 5 questions for 40 marks, students are supposed to answer all the questions there. Then in section B, where there are 4 questions, students are supposed to answer 3 there for 60 marks. I have a video where we have solved all the section A, and also another video where we solve the question 6 and the question 7 in the section B. Please, if you have not watched that video, try to watch it, or you can get a link to that video in my description box. So today's video, we'll look at the question 8 and the question 9. This will be a very interesting engagement, so please come along. So the question A says that give the general solution of the differential equation y prime prime plus y equals to tan x. So this is a second order ordinary differential equation. Anytime we are faced with a second order ordinary differential equation problem, 2 questions comes into mind. Is the differential equation homogeneous or it is non-homogeneous? It becomes homogeneous if the differential is equated to 0. However, it becomes non-homogeneous if it is equated to another function of x. And this function here is tan x. So it is non-homogeneous. Also, anytime we are faced with a non-homogeneous differential equations, there are 3 methods that we use to solve. That's method of undetermined coefficient, variation of parameters, and the D operator method. So in this problem, I'm going to use the method of variation of parameters to solve this differential equation. So we said that the general solution to a non-homogeneous differential equation y of x will be equal to the complementary solution to the homogeneous side plus the solution to the non-homogeneous side. So how do we make this equation homogeneous? We equate this to 0. So when we set it up to 0 like this, then it becomes homogeneous. Then we will use the method of the homogeneous, how to solve homogeneous solutions to solve it. So in this, we'll let y to be equal to e exponent r of x, where r is the independent variable. So our y prime will be, where x is the independent variable, sorry. So our y prime will be equal to r e exponent r of x, and y prime prime will be equal to r square e exponent r of x. Now we substitute this into the differential equation. So our y prime prime is r square e exponent r of x plus our y, which is e exponent r of x, all that equal to 0. So you can see r of x is common to both sides, to these 2 terms. So we factor it out. So here r squared plus 1 multiplied by e exponent r of x will be equal to 0. And then our r squared plus 1 will be equal to 0 when we divide both sides by e exponent r of x. Now this becomes a quadratic equation. And the nature of root of the quadratic equation will determine the general form for this equation, for this differential equation. So our r squared will be equal to -1. So our r will be equal to plus or minus the square root of -1. And that will be equal to plus or minus I. So this, the root to this quadratic equation is complex. So we say it's a complex root system. Then the general form for the homogeneous aspect of the differential equation this will be y of c will be equal to e exponent lambda x bracket a cos beta x, then plus b sine beta x, where our lambda here is the real part of the complex root, and the real part here is 0, and the beta is the coefficient of, where the beta is the coefficient of the complex system. So the coefficient here is 1, and the lambda will be 0. So y of c is equal to e exponent 0x a cos x plus b sine x. And this will be 0, so that will be 1. Then we can say the general solution to the complementary side, y of c is just a cos x plus b sine x. So now we'll find the general solution to the non-homogeneous side, that's y of p, using the method of undetermined coefficient. So with the method of undetermined coefficient, we say our y of p is given as negative y1 integral of y2 g of x over the Roskian of y1 comma y2 dx, then plus y2 integral of y1 g of x, the Roskian of y1 comma y2 d of x. So what's our y1? Our y1 is just the coefficient of the a here, which is cos x, and our y2 will be equal to sine x, and our g of x becomes the non-homogeneous side, which is what? Tan x. So we'll find the Roskian now. We say the Roskian of y1 comma y2 will be equal to. Please check out my videos on how to find the Roskian of 2 functions and 3 functions. A function that is dependent on 2 variables and 3 variables on YouTube. So we can say the Roskian of y1, y2 will be equal to the y1, which is cos x, and the y2, which is sine x, plus their differentials. So the differential of cos will be negative sine x, and the differential of sine will be cos x. Then this becomes a 2 by 2 matrix, which we are finding the determinant for. So we can say the Roskian of y1 comma y2 will be equal to this times this, which is cos square x, then minus this times this, which will be plus sine square x. And remember, cos square x plus sine square x is nothing but 1. So we say the Roskian of y1 and y2 is 1. So we'll now substitute that into this to find our y of p. So you can say our y of p will be equal to negative y1, which is, that will be negative cos s, integral of y2, which is sine x, then g of s is what? Tan x. Then divided by the Roskian of y1 and y2, which is 1, so it will not have any effect. Then plus, so dx, then plus y2, which is sine x, integral of y1, which is cos x, then tan x, which is g of x dx, divided by the Roskian, which is 1, and it will not have any effect. So you can say our yp will be equal to negative cos x, integral of sine x. Remember, tan x is what? Sine x over cos x dx, plus sine x, integral of cos x, then sine x over cos x dx. So from here we can say our y of p will be equal to negative cos x, integral of sin x times sin x will be sine square x over cos x dx plus sin x integral of, so cos x will divide this cos x, will be left with just sin x there dx. So we can rewrite this as negative cos x integral of. So remember, sine square x will be 1 minus cos square x all over cos x dx plus sine x integral of sine x dx. Can go further to say our y of p will be equal to negative cos x integral of 1 over cos x dx. I'm splitting into half a common denominator, then minus cos square x, that's integral of cos square x over cos x dx, then plus our sine x integral of sine x dx. So our y of p will be equal to negative cos x multiplied by the integral of 1 over cos x dx, then minus this will give us cos square x divided by cos x will just be cos x dx, then plus sine x integral of sine x dx. So look at it, we can find the integral of cos x. We know that is sine x. Integral of sine x is negative cos x out of integral of 1 over cos x. So the integral of 1 over cos x, so integral of 1 over cos x dx is giving us half ln of absolute value of 1 plus sine x over 1 minus sine x. So please check out my videos on how to integrate or find the integral of 1 over cos x on YouTube, or you can get a link to that video in my description box. So we can say our y of p will be equal to negative cos x times the integral. Remember I said the integral of 1 over cos x dx will be half ln of absolute value of 1 plus sine x over 1 minus sine x. So minus the integral of cos x is sine x, then plus sine x, the integral of sine x is negative cos x, then plus our constant of integration. So our y of p will be equal to, when we distribute this, we'll get negative half cos x ln the absolute value of 1 plus sine x over 1 minus sine x. Then this times that to be plus sine x cos x. Then this will give us minus sine x cos x, then plus our constant of integration. So our y of p will be equal to negative half cos ln the absolute value of 1 plus sine x over 1 minus sine x. Then sine x cos x minus sine x cos x will be 0, so plus that's the constant. So this becomes our y of p. So we can say our y of p then is negative half cos ln of the absolute value of 1 plus sine x over 1 minus sine x, then plus c. So with the principle of superposition, we join the two together, then that becomes the general solution to our differential equation. So the general solution to our differential equation, y will be equal to y of x. Remember, we said it's equal to y of c, which is a cos x plus b sine x. Then we'll add this, so we say minus half cos ln the absolute value of 1 plus sine x over 1 minus sine x, then plus our constant of integration. Then this becomes our general solution to this differential equation. I hope you get that. We'll go to the ninth question. So the ninth aspect, the A shows that the Laplace transform of E lambda t is equal to 1 over s minus lambda. That is, the Laplace of E lambda t is equal to 1 over s minus lambda. So this question is on Laplace transform. So a differential equation mostly comes with Laplace transform. So we said that the Laplace transform of any function f of x, okay, is giving us the integral spanning from 0 to infinity of e negative st times the function, that's f of t. Let's say t, so f of t dt. So this is the Laplace transform for any function. So we can say that f of t here, our f of t here, is equal to what? E exponent lambda t. So we just substitute. So we can say the Laplace transform of e exponent lambda t is equal to the integral spanning from 0 to infinity of e exponent negative st times e exponent lambda t dt. So we can say this is the integral spanning from 0 to infinity. So we'll use indices to join this. We'll say e exponent lambda t minus st. So I'm adding the two, positive minus the negative, dt. This can be rewritten as integral spanning from 0 to infinity of e bracket lambda minus s all times t dt. I just factor out the t. So we need to integrate this exponential function. Remember how to integrate this exponential function. We differentiate the exponent and use it to divide the function. And the differential of this will just be lambda minus s. So we can say this is equal to e exponent lambda minus s all times t divided by lambda minus s. That will be the integral spanning from 0 to infinite. Remember, this is a definite integral, so there will not be any constant of integration. So now we substitute the limiting point to find our value. So this will be equal to e exponent lambda minus s all times infinity over lambda minus s, then minus e exponent lambda minus s all times 0 over lambda minus s. So what are we having? So this will be, when we manipulate this, the whole of this will be 0. So it says 0 minus, and this will be e exponent 0, which is 1. 0 minus 1 all over lambda minus s. So this will be negative 1 over lambda minus s. So when we multiply the top, both the numerator and the denominator by negative, we will say that the Laplace transform of e exponent lambda t will be equal to the top, that will be 1, then minus this will become positive, so s, then minus this will become negative, minus lambda. I hope you get that. So that's why the question says we should show. So we are able to show that. So the Laplace transform of any exponential function simply is just the constant here, 1 over 1 all over s minus the constant here. So it's very simple. So if they ask you maybe the Laplace transform of e exponent 6t, the answer will just be 1 over s minus 6. It's as simple as that. So the B aspect says we should show that the Laplace of 1 is nothing but 1 over s. It's very true. Remember we said Laplace of any function f of maybe t is equal to integral spanning from 0 to infinity of e exponent negative st times the function dt. So the function in this case is 1. So we can say our f of t here is 1. That's the Laplace of a constant. So at the end of the question, you see that the Laplace of every constant is just a constant over s. So we say that the Laplace of 1, the function is 1, will be equal to the integral spanning from 0 to infinity of e exponent negative st, then times 1 dt. So this will be integral spanning from 0 to infinity e exponent negative st dt. Now we need to integrate that. Very simple. We'll differentiate this. We'll get negative s and use it to divide. So we say e exponent negative st divided by negative s spanning from 0 to infinity. So when we solve further, I will say this will be equal to e exponent negative s times infinity over s, negative s, then minus e exponent negative s times 0 over negative s. I hope you get that. So when we manipulate this, remember we'll get something 1 over infinity, and that will give us 0. So the whole of this will be 0. So I have 0, then minus minus, so plus, the top will be 1 over s. So this will be equal to 1 over our s. Then it's simply that the Laplace of 1 is 1 over s. So it's very true. The Laplace of any constant a is equal to 1 is equal to the constant over s. So you can say the Laplace of 6 is equal to 6 over s. I hope you get that. We'll go to the C aspect of the question 9. So the C aspect of the question 9 says we should derive the Laplace transform for Laplace 3 minus e exponent negative 3t plus 5, please this is 5, plus 5 sine 2t, and show that the result is 3 over s minus 1 over s plus 3 plus 10 over s squared plus 4. So remember, we learned that the Laplace of any constant is that constant over s. And the Laplace of an exponential function, e exponent lambda t, is just equal to 1 over s minus the coefficient here, that's the lambda. I hope you get that. However, the Laplace of the function sine at, that's the Laplace of any sine function, at will be equal to, see the constant here, that's a over s squared plus the constant square. So we can say that the Laplace of the question that is given to us, that's 3 minus e exponent negative 3t plus 5 sine 2t will be equal to the Laplace of each of the term. So that will be Laplace of 3 minus the Laplace of e exponent negative 3t, then plus 5 the Laplace of sine 2t. So that's how we do it. So remember, we said the Laplace of a constant is the constant over s. Then we can say that the Laplace of 3 will just be 3 over s for the first one, minus, remember also we said the Laplace of an exponential function is 1 minus s minus the coefficient of the exponent, the variable t, the coefficient of the variable t of the exponent. So we can say that the coefficient of the variable t is the negative 3. So the Laplace of e exponent negative 3t will be equal to 1 over s minus negative 3. I hope you get that. That's it. Then plus 5 the Laplace of sine 2t. So we say the Laplace of a constant times sine a constant times t will be the constant over s squared plus the constant square. And our constant in that case is 2. I hope you get that. So we can say that the Laplace of sine 2t will be equal to 2 over s squared plus 2 squared. This is very interesting. So this will be equal to 3 over s minus 1 over x plus 3. Then plus 5 times 2 will be 10. So 10 all over s squared. Then plus 2 squared is 4. So we have proved that. We have shown that. Then we can say the Laplace of the function will be equal to 3 over s minus 1 over s plus 3 plus 10 over s squared plus 4 as required. So this is very interesting. So we have come to the end of our question solving mission. I will indulge you to subscribe to my YouTube channel. Share the video with your friends and encourage them to subscribe. Until we meet again, my name is Kepsi.